So a couple of household that is for Ishmael is our tutor. Let's get this. Right, he's going to be our tutor again. And I believe also we're going to have someone else as well, access to Sativa. And that sounds really, we're going to have access to Sativa. That's her name. Because as you can see, Ishmael's schedule is a little inconvenient for our Tuesday, Thursday meetings. Ishmael's our embedded tutor, Ishmael Perez, Mondays and Wednesdays from 2 to 3. And that's R1B, it looks like. And STEM Center, Mondays and Wednesdays from 10 to 2. And they're going to start on Tuesday next week. Why would he start on Tuesday? If he's on Mondays and Wednesdays, okay, tutoring itself in these places for anything, there's other people there on Tuesdays and Thursdays. His class schedule is his own class schedule, doesn't allow him to tutor basically on Tuesdays and Thursdays. But you got to remember, I have office hours every day, Monday through Thursday from 7:30 to 8:20. Now I know that you guys may not be here that early, but if you are, I'm here. I'm in here. And I also have an office hour before this class meets from 11 to 11:50, because I have a class that goes from 8:30 to 10:45. And then so if my 10:45 student class gets out and they want to stick around from 11 to 11:50, they can come in or they can stay and get help. And it's before this class, you guys can come in early. And if you have a class going on and you can't make it, so I'll be right in here. I'm going to stay in here from 12 to 12:30 anyway. Pop in if I'm in here, that's fine. Okay, no big deal. And then by request, I can Zoom an office hour on Friday. You just got to let me know with an email. Hey, can we do a Zoom on Friday? And I'll set that up. But it's by request as needed. Don't have Sativa's scheduled yet. She's supposed to come and introduce herself and everything. So that'll hopefully happen next week. Okay. There will be flyers posted as soon as I get the flyers from the students themselves. But even though if you don't see Ishmael, there's other people in the STEM Center that can help. It's all free. Okay, it's all free. Work with each other. Get to know people, because that's how you become proficient. It's a language. You got to start speaking it. If all you do is read and try to do the problems and you never make the connection where you're talking it out loud, you're saying it to yourself, you're whatever, you just sit there and you try to do the problem, read and write, it's not going to ever translate from the reading, from the visual through your brain, and where it comes out auditory and you're explaining it to someone else. It makes a difference. Okay, one little piece of advice that I give my lower level classes, and I even give it to Trig and now you guys. When you're working a problem, I've had students tell me, when you do it on the board, it makes sense. I understand what you're doing when you do it on the board. Then when I have to go home and do it, I can't remember. I don't have a clue. And I say, well, that's because when I'm doing it on the board, I'm verbally cueing you as we go through the steps. What do we do next? We basically are talking it through. So you're hearing it as we do it. When you go home and do that, you're not hearing it anymore. You're just trying to do it and you hope you can figure it out, but you're not hearing it. So my advice is, it's time to start talking to yourself. Mumble. In a classroom setting, in a test setting, you can't talk out loud, but you get the little squirrel talking to yourself in your brain, or you need to mumble under your breath. And that will help. It really will help. My mom did not have a great education. I think she graduated high school in 1938. And she always said the only reason she went to school, her father did not want her going to school in the first place. Okay, there's no reason for women to go to school. It's her dad's, mentality. But she was there because that's where the guys were. My mom was a big flirt, but she kept telling me, "Thanks, Mom, I didn't need to know that."
That's what they call them.
Yeah.
MRS.
Yeah, well, yeah. My grandfather was a musician. And so her favorite day was Sunday because at the dance hall, she would get to go and it was just dancing. That's all, And so he was a mariachi musician and that's all she lived for, just to go on Sunday to the dance. And when the war started, World War II, they would go out and wave to the troops. They would go by in the trains. This was in Arizona. But growing up, my mom was always the accountant or bookkeeper for all of the clubs that she belonged to. Choir, YLI, which is the Young Ladies Institute, which means she was 7 young ladies. It always knocks some more on me. But the Guadalupe Society, she was always in charge of the money. She could not use a calculator because she didn't understand how a calculator works. Never saw her really use pencil and paper. When she did the math, she counted on her fingers, and the only time she ever spoke Spanish in the house. My parents never spoke Spanish in the house, ever. Only my oldest sister, the firstborn, she's the only one that can speak Spanish because she went and made it a point to learn when she was, 34. My grandfather would not allow English in his house. You had to speak Spanish. In our house, my mom and dad decided we're only going to speak English because my dad, who was born in the United States, but the rest of the family was born in Mexico in 1919, when he spoke Spanish going to school here in the United States, he was beaten by the teachers. And he didn't want his kids to ever experience anything like that. So that's why I cannot speak Spanish at all. But that's a side tangent. She would count, and the only time she ever spoke Spanish out loud was, or when they were yelling at each other, she would count in Spanish and she would do it on her fingers. And she kept all the books out because that's the process of hearing it, seeing it, whatever it takes. So if you haven't tried a different strategy, what you're doing isn't working. Time for a different strategy. Time to apply something else. I was really good at math all the way through high school. And then I got to college and all of a sudden, it's like, oh my gosh, why isn't this easy? Through high school, I was able to study and work, do my homework as I watched TV. I didn't need to concentrate that much to do the work. Well, college is different. When I got into college, I stopped working in front of the TV. I would go to the library at Fresno State, or when I was at UCLA, I would go into the stacks at the library at UCLA. And that's when I would just say, hey, you know what? For these 4, 3, 5 hours, whatever time, block of time, I'm going to go and focus and get this stuff done so I don't have to worry about it anymore. I got to get rid of the distractions. Because I can't do it. Some of you, if you got chaos going on at home, sometimes you need a place to go where you might need to access help right in front of you, or just a quieter place to work. And that's another thing that this is available for. You can just hang out here and get it done. And you also start to build a rapport with other types of students who are going in your educational direction. Okay? And it's networking. It's grouping and networking. That's the key Yeah, it's who you know sometimes. Okay. All right, there's the shield. Now I'm winning. Okay, so we're gonna be talking about graphing, and we're gonna be doing some crazy looking graphs in this class. So this is what I would do then. For those of you who might have had me in 103 or even 201 once upon a time. This is all we worried about. I used this -7 to 7 grid, and everything I taught was basically in that type of a grid. I never gave any problem that needed to be graphed that wouldn't fit into -7 to +7 XY axis. Problem is, in this class, we're going to need a little bigger type of an XY axis. So this one, and I don't expect you to go and find graph paper or buy graph paper. All I did was Google coordinate axis. And then I didn't just like look at the websites, I looked at pictures. Go to the pictures. And then I just clicked on a picture, copied it and printed it, put it on an MS Word document. And what I'm going to do is, I haven't done this yet, is I will make, and I won't put 3 by 4 because right here, this is 12 of those 7 by 7s. What I'm going to do is I'm going to do 4, and I will make graph paper so you don't have to buy your own, and I'll print those out, a few of them, and I'll also post it on the Canvas page in case you need to print out more, but I'll have some ready to go next Tuesday, and I'll give you at least 2 or 3 copies of it, and that'll get you a way to plot accurate graphs, plot and label good graphs, because if you don't have an XY axis, it's really hard to draw a really good graph. Okay, if you're just guessing and drawing it by freehand, it doesn't come out really nice. That's why we'll do this. I don't know how I'm going to put that. Yeah, just shrink it there. Just because I'm not sure everybody is familiar with the XY axis. I can't take anything for granted. Okay. So I have to pause the recording because this is copyright material. So I'm just going to highlight some of the things that are going to happen in the course itself. 3 basic types of functions that are proven to be the most important in modeling real life situations. Real life. That's what this is about. Taking mathematics and when am I ever going to have to use this? When students ask that question as they're growing up, when am I ever going to have to use this? All I can do is look at them all the way through Algebra 2 going, I really can't explain it to you because you don't have enough background yet. Not until you get past Algebra 2 can I actually give you some information about how it's going to apply, how you can put the things together. Okay. I remember my first year teaching geometry, so I wasn't, I wasn't great at it, but geometry, I had a student, Natalie was her name, and she said, when are we going to use this? And I said, Natalie, she wasn't a great student. You're probably never going to use this. Trying to be honest with her. I don't see you ever using geometry. But you got to pass the class in order to that. You got to use it on Friday's test. Okay, let's get through that, and then we'll think about later on how we'll apply, how to open up whatever doors you might want to have open. But these functions model real-life situations. These functions are algebraic, exponential, logarithmic, trigonometric, inverse trig. These three types of functions are referred to as elementary. Okay, the beginning, the not so elementary like, oh, everybody should know them or should already just know them. Elementary in terms of the building blocks, and often placed in two categories, algebraic and transcendental. So the elementary functions that we should know are algebraic, and then the second type is transcendental. Okay, we're going to focus on the algebraic today, but I'm just going to show you how it does break down, what they do look like, and what they're comprised of. I'll make this fit a little bit better. Algebraic, and I'm going to go over what these look like and give you an idea, and then we're going to really hit how to work with these next week. But f of x is x to the first, x squared, x to the third, rational fractions, square roots. Those are the ones I'm going to focus on today. But just to give you an idea of where it goes. The train. Huh? Well, never had a problem with it before, so I don't know why I'm having a problem with it now. It's a problem. The transcendental and you'll see that we're not going to get most of these in this 3A. The two that we're going to hit are exponential and logarithmic in chapter 4. These other transcendental, sine, cosine, tangent, secant, cosecant, cotangent, and the inverse trigs are sine, arc, cosine, arctangent. This is in the Math 4A class. Okay? So you're not going to need to worry about those. Not in this class, not in 3A. In trig, that's when we do trig in 4A. No, we're not doing so. The trigonometry class is Math 4A. Well, there's not enough time in a one semester class to do all of it. That's the deal. If it was a year-long class, then we would spend one semester doing just the trig, and the other part of the semester doing just the college algebra. Yeah, it is, but either that or I go so fast that nothing gets explained. And that's where everybody's at a different level of understanding. And I don't like doing that. I never assume that everybody knows exactly what I'm talking about. It's coming from the same background. So unless somebody says, "Could you say that again?" I try to keep, I judge by expressions on people's faces, or at least in their eyes. If I'm seeing the tops of their heads, I know I can go a little faster because they're asleep. Okay. But yeah, this is what we cover in the Math 4A class. And you can take 3A before 4A, 4A before 3A, it doesn't matter because they're separate. Some people are taking 3A and 4A at the same time. I know, yeah, exactly. We will be doing in chapter 1, non-elementary, okay, absolute value, okay, and greatest integer function, which is also known as a step function. Absolute value and greatest integer. Now, the reason why they're non-elementary is because their shapes are, when you look at it with the language of calculus, we would say the absolute value function is continuous, which means as you go from left to right, there's on the given domain, there's no holes in the graph. It doesn't have a hole in it. There's no breaks in it. Every value of X has a Y value that corresponds to it. But the problem with absolute value is it's non-differentiable at a certain point. There's no way you can take a derivative. Absolute value has a sharp corner. There's no derivative at the sharp corner, so that's why it's not elementary. The greatest integer function is a step function. So it's not continuous. As you move from this step and then go to this step, it's broken. And so that missing piece means you have a discontinuity at that one given point. Therefore, that's what makes it non-elementary. All of the elementary functions, there's no breaks in it and they're nice and smooth all the time, the elementary ones. Okay? So the intro that you're going to get today is based on the algebraic. I posted the assignment sheet on Canvas. And here's my problem is I printed the assignment sheet so I could make copies for everyone and give you a copy today. Unfortunately, I left my office keys at home. So I can't go into the office and actually get the print to go down to make the copies to give you so I will have your copies made for you on Tuesday. I apologize. I haven't slept much in the last week and it's starting to accumulate in terms of motor neurons and receptors misfiring and yeah. So just so we make sure we're clear, homework's not due until the day we take the exam. I haven't set that date yet, so just don't worry about it. When you see the EOO, it means every other odd. Do 5, skip 7, do 9, skip 11, stop at 13. This is 17 to 22 all. Anytime I do something like an all, it's usually like I'm matching. If you look at 17 to 22 here, just so you can see, 1.1. Basically, it wants you to, which of these equations matches to the given A through F picture. So like 17 is 2 times the square root of X. So which one would be a picture of 2 times the square root of X? That's B. Okay. You don't have to graph it on your own. You should be able to look at, I know what this is supposed to look like, and there's only one of these pictures that looks like a square root graph. And I will go over what that means today. Back to 23 to 55, every other odd. Now I put 45 out of order because I want you to, you should try to do 45 because it's got some good application to it. And then just 61 and 63 and the rest of them The review sheet itself, it's never meant for you to turn in. It's just a matter of I will give you a review sheet 2 days before we ever take a test. Then the day before the test, we review for the test by going over the review sheet. And this is what I showed you. Homework, You're going to score your own homework out of 10 points for each section. Give yourself an honest, assessment. You deserve, 10 out of 10, 9 out of 10, 8 out of 10. If you think you deserve 7.5, round up to 8. Let's not do decimals. It's just a pain. It's not pain for me, but I've had students not have the decimals correctly. Okay, then I feel like I got to take off points down here because you didn't have the decimals right. Okay, so each section you score out of 10, add them up. What did you get out of the 7 sections out of 70? Then I'm going to score how well I think you scored your own homework out of 20. So then the total homework for this chapter 1 is out of 90. This one and this one, your total out of 90. Let's just get 90 out of 90, call it good. Makes my life easy. Will hopefully make your life easy too. But that's the cover sheet. And again, I'll print this out for you unless you want to print out your own. I'll print this out for you and have it for you. Handle home. Okay. Back to here. And I'm going to do this. Okay. All right. So that first one, linear. A function, and these are the parent functions. That means what we're going to do with these parent functions, this is the basic shape that the function will always take until we decide to change possibly the shift left and right, shift up or down. We might reflect it across the x-axis. We might reflect it across the y-axis. We could reflect it across the x and the y-axis. We might stretch it sideways. We might stretch it vertically. Okay, we might squish it. We can do all sorts of manipulation, but this is the simplest version of those different types of graphs. The breakdown is, the first one is linear. F of x equals x to the first. A linear function. And the reason why it's linear is because it will always make a straight line. X to the first, it's a power of 1. One-dimensional. One-dimensional linear. Okay? So when you look at this, you're looking at basically just y equals x. Which means the slope is 1 times x plus, if you think about y equals mx plus b, the y-intercept right here is 0. So it would go through here, and then our slope is 1 over 1. We go up 1 over 1, up 1 over 1, up 1 over 1. An important piece of technology that was invented, I don't know, 6,000 years ago. Not a ruler, just a straight edge. Just something straight. When you graph and you need to make something straight, use a straight edge. You'll find out that I'm much more pleasant when people graph things nicely. Much more generous with partial credit when you graph things nicely. Now, if you don't want to have a ruler, there it goes. You got your ATM card, your ID card, whatever you need. It's a straight edge. That's all you need. Okay. We change the position by changing the value of e, vertical change. We can change the horizontal change Okay, not really unless you do something with the x. That will change it in here. You can change the pitch or the slope of the line by changing what's in front. But there's not a whole lot we can do with just linear. Then it gets a little interesting. I get into some real life application. F of x equals x squared, the quadratic. When you have a power of 2, it's a quadratic function. So if you took math 103, we graph quadratics, we graph x squared. One of the first things we do is a brand new graph. And we basically learn how to graph new things by plugging in numbers. If I plug in -3, -3, when you substitute -3 into this function, parentheses, -3 squared. Because if you don't put parentheses around the negative, you won't be squaring the negative. If all you do is go -3 and then square it, -3 squared is -9. You're substituting -3 for the x, so you're supposed to square all of it. That means negative times negative, 3 times 3, you get +9. So when -3 goes in, we get +9 out. So it's up here. And when we plug in -2, -2 squared is +4. And when we plug in -1, -1 to the second is +1. 0 squared is 0. So that's at the origin. And on this left-hand side, when you want to try to connect points, you can see those points are not all on the same line anymore. You can't draw just a single line to all the points, so it's not linear anymore. You connect them with a nice smooth curve. On the right-hand side, 1 squared. 1 squared is +1. So now you have something called symmetry. Here's the y-axis. You have symmetry about the y-axis. 2 goes in. 2 squared is +4. When 3 goes in, it's the same as -3, symmetry across the y-axis. No matter what, when you graph something that is a power of 2, it takes on this shape. It's a curve. That continually increases as you go further to the left. It's going to increase toward positive infinity. And as you go to the right, it's going to increase to positive infinity. And I need a little much better than that, but my shoulder is not going to allow me to do that until I get it worked on. This is what I have to tell Algebra Math 103 students. You don't just go straight up. Don't be lazy, because you're going to continually plug in numbers left, or right. So you're going to have a value above the 4, a value above the 5, it's not going to go straight up and stay above 2. As you continue moving to the right, the y's keep going higher and higher. So there is this effect. Okay? This effect. Can't just go straight up. It wouldn't be a function if it went straight up. That's a parabola. Any equation, any quadratic equation, power of 2, a degree of 2, is going to graph like a parabola. Always. It'll have a parabolic shape. And we're really going to break down the pieces of a parabola conic section later on. What makes all the conic sections come out. If you do this. Put a minus in front of the x squared. When I plug in -3, that negative is not part of what's being squared. It's the coefficient of that squared. So the negative is out in front. And then you substitute and replace this x with -3, and that's what you square. Okay, you gotta be, the details matter. So what we end up with is f of -3 is equal to, there's a negative in front of this positive 9. So what does the negative in front of the x squared do to the old picture? When -3 goes in, instead of getting +9, it's down here at -9. Yeah, so it's moving, it flips all those positive answers. And now because of the negative on the outside, they all become negative answers. It reflects it across the x-axis. This is true for every kind of graph that we have here. If you put a negative in front of any of these functions, what was positive is now going to flip down below the x-axis and become a negative value. If it was negative, an extra negative in front would flip up and become a positive value. A negative in front is going to cause a reflection across the x-axis. Okay, it's always going to flip it vertically. So that's going to flip down. When I plug in -2, I would get -4 instead. When I plug in -1, I would get -1. 0 would still give me 0. When I plug in +1, I would get -1. When I plug in +2, I would get -4. When I plug in +3, I would get -9. And so now the parabola is going to open down instead of opening up. Quadratic equations, for the most part, are very important in terms of finding maximum and maximum sales versus minimum cost. When are we going to maximize our sales with a minimum cost effort in business? If you can model what's going on with your cost analysis and your profit analysis, you can come up with an equation with the given set of data that's quadratic, or maybe it's a cubic. But you can find out where the maximums and the minimums are happening. When are your sales increasing? Supply and demand, that's one of the basic foundations of economics. If you if you make too much of something, the supply is so great, everybody has one. So the sales are going to start to go down and you start to lose money because you've made too many of them. That's what caused the baseball card crisis in 1987 through about 1995. They started making so many of the same baseball cards. Everybody's got a Barry Bonds. Nobody wants one. Well, nobody wants one now anyway, but everybody's got one. Sorry. That's 14. That's what it's about. My team's better at 14. It's all. Anyway. But that's what caused it to crash. Same thing with comics. This is my life reference here. Baseball cards, comics. Baseball cards, comics. In the 1990s, they started making, and they still unfortunately do, they made 5 different covers for the same freaking book. Thinking, oh yeah, they'll buy the same book 5 different times because they gotta have those covers. They're playing on my obsessive compulsive disease. Yeah, they are. But not everybody can afford that. So then the market crashes. Or everybody has one of those. So they made so many of them, nobody wants them anymore. And everything crashes. They're not worth anything. People stop buying. Supply and demand. Why is gas so high? Well, the pandemic, nobody was driving. They had all that gasoline, and the gas didn't cost that much during the pandemic because, well, there was all this supply. So they lowered the price because they had to get rid of all that gasoline. Now everybody's driving. The supply is not as high as it used to be, so the demand is up, so they can raise the price. Economics. Or it's a conspiracy theory. You make it, check it out. But more important, life. That upside down x squared is why this flies through the air in a parabolic motion. Anything you throw through the air will always take the shape of a parabola, always. The time it takes for me to throw this and for it to reach its maximum height is exactly the same time it takes for the maximum height to hit back down to the ground. The exact same time this way is the exact same time that way. Even if I go throw it straight up, the time it took for it to go straight up is exactly the same amount of time as it took for it to come back down. The only thing affecting it is my initial velocity, and then gravity slows it down. At the very top, at its maximum height, its velocity in the positive direction is 0. And then it starts to come back where it starts to gain negative velocity because it's going down. So positive velocity on the way up. As it's going up, the velocity is getting weaker, so it's getting smaller until it reaches a velocity of 0 at the top. And then a velocity starts to become a little bit greater, it's going faster. But it's going to hit my hand with the same amount of velocity as what I released it. Because it's a perfect parabola, even though it went straight up, straight down. If I did the same thing but was moving, you saw relativity. The shape from your perspective was a parabola, but to me, it was just straight up and down. Relatively speaking, that's where Einstein was able to make the mind game connection into theory of relativity. What's going on from my perspective is not the same thing for everybody. One aspect of relativity, the greater your acceleration, time is not the same for everybody. The greater your acceleration is, time is flowing much more slowly for you than if you're just standing still. So in other words, as you drive to school, you're in a state of acceleration. So as you drive to school, you are aging more slowly than when you're just sitting at school. Because it's minuscule. They took two twins. One went up into space, lots of acceleration. All that time in space, they had synchronous quantum watches, not quantum watches, atomic watches on an atomic scale. Basically, you measure the time of the vibration of the cesium atom. The cesium atom watch was behind the one that the twin that stayed on the ground, which means the twin that was on the ground was older than the twin that went up into space. By whatever, few seconds, few minutes, it depends. So the theory of relativity says if you were to launch from here and go out into space, maybe if you're going to be one of those people that get to go and start heading towards the speed of light. If you were gone, according to you, 5 months, a year, you come back, everybody's dead.
Isn't that the same theory they use in the movie Interstellar?
A little bit, yeah, because, well, that was a wormhole. But the concept was when they got to the big giant, the big gravity giant, when they went down to the surface, the person who stayed in orbit, it was like 17 years for him as they waited for those people who spent like 4 hours on the surface of that big water giant. But that guy was alone for 17 years in the spacecraft.
So did the same thing on American reality.
The what?
On an American reality.
Oh, I need to, that's on Star. I love Neil Gaiman. And he's the one who came up with American Gods.
Oh, American Dad.
Oh, American Dad, American Dad, I got you.
I thought.
But you know what? Seth MacFarlane, he does write some really smart stuff. And The Simpsons. Simpsons was family time in our household when the kids were growing up. The original writers, I don't know about right now, but the original writers of The Simpsons were math majors from Harvard and Boston University. Math majors. There's an actual website dedicated to all the math that is in all of the Simpsons episodes for the entire, I don't know what else, season 28. Yeah. So I was always saying Simpsons is one of the most intelligent TV shows you could possibly watch. Okay. But the flight of any object. Parabolic, the reason why we can launch into orbit, here's the Earth. If I throw a ball, it takes the path of a parabola and hits the Earth. Because I can't throw it fast enough. I have to achieve escape velocity from the Earth's gravitational attraction. If I throw it faster, then it's going to land a little bit further. If I can throw it faster, it'll land a little bit further. Rockets, the space shuttle, would launch and achieve a velocity of 17,500 miles per hour. That's how fast the International Space Station goes to stay in orbit around the Earth. 17,500 miles per hour. But it's not just staying in orbit, it's slowly all the time, falling towards the Earth. Every so often, they have to fire their, they're not rockets, but they're just correctional thrusters to raise their altitude. Because the attraction is always going to spiral it back into the Earth. So if they don't fire those things, it's going to hit the Earth. So what happens is if you launch at 17,500 miles, then what happens, instead of falling into the Earth, you just miss the Earth. And if you can stay at that velocity, you just keep on, as you go around, instead of falling into the Earth, you just keep on missing the Earth. And that's when you can achieve orbit. And when you want to go to the moon, after you're in orbit, you need to fire your rocket and go faster. You need to approach about 36,000 miles per hour. Okay? But that's how it works. When Bugs Bunny threw that baseball and it went all the way around the earth and the batter missed it and had all those little stickers from all the other countries, he had to throw it over 17,500 miles an hour to get that baseball to go around the earth. You guys watch the movie Tunes for way
What
later.
about now? But it's like, so try to go to the moon and go over the earth. And then shoot the moon?
Well, yeah, you go around the earth and you help gravity taking you around the earth and increase your velocity a little bit, and then because you got to orient yourself. And just first of all, you want to launch, go into orbit, make sure everything's okay, and then you want to go back then, especially.
They don't just automatically go up in the air.
Yeah, well, airplanes, we have atmosphere, and we have the lift of the atmosphere, the air that keeps an airplane in the sky. The faster you go, you don't need as much lift because now you're a rocket. So a rocket, and the rockets will go up and eventually they'll start to curve. And you'll hear when you watch a launch, they'll say an altitude of and downrange. Because when it launches, you'll hear altitude, so total height, but downrange from, because you can't just go up. It's not like Star Wars, Star Trek, where they just go up and leave the Earth. They have to go up and start to get into orbit. They have to go this way. Why did we launch from Kennedy in Florida? For a couple of reasons. You got water around you in case you need to abort. But number two, the closer you can get to the equator. The Earth is spinning faster at the equator, or your velocity at the equator is a lot faster than your velocity in Alaska, because the circumference at the equator is greater than the circumference that you're spinning at Alaska. So the velocity that you're already spinning is going to help launch whatever you're in as an assist. Okay. Mathematically, they think of all these things before it happens. What always amazed me is mathematically, they're able to telescope, spot a comet, predict, and when they see a comet, that's where the comet was, let's say, an hour and a half ago, if it's within our solar system. Maybe the sun is 8 light minutes away, so it takes light 8 minutes to get. Maybe that's where that comet was 20 minutes ago, 15 minutes ago, if it's really far away. It's out past Saturn, past Neptune. So they spot the comet. And then we've had space probes that we've been able to launch that have been able to use their trajectory, catch up to the comet, land on the comet. 4 months, no, sorry, not 4 months, that's 16 months from now. So they're able to predict where that comet will be, and they're able to predict where this rocket needs to go, how it needs to use the moon, maybe, or the Earth, or even maybe make a orbit around Mars to get a gravity assist, to get the speed necessary to be able to land on whatever comet it is. That's what has basically amazed me in terms of what we've been able to accomplish. Scientifically, engineering-wise. There is one thing that did happen. We talk about in the United States, we ain't so big on metric. In the 70s growing up, we tried. Nobody really bought into it. There was a Mars space probe in the last 10 years that basically burned up in the atmosphere because the United States, I think we built the space probe, the Europeans built the spacecraft, or vice versa. Europeans, they did everything in metric. We did our stuff in feet, miles. So the language, the measurements didn't jive. And when they got to Mars, it kind of had a faulty logic and it crashed. You know, $4 billion later. Because they didn't check their map. Yeah. Didn't want to be that guy. Okay, so parabolas. Parabolas control this. Your eyeball is a parabola. The reason why you can see, the reason why my glasses work is because the glasses as a parabola take in the parallel beams of light, and instead of my eyeball, my lens, the parabola that's basically screwed up, focusing the light beam where it's not supposed to be, the corrective lens focuses the light beam on my retina and on my optic nerve so I can see. Contact lens, LASIK surgery. They used to cut the lens off your eye, called radiokeratotomy. They would freeze it, then they would basically make little slices and then put it back onto your eyeball. Now, you don't have any pain nerves on your eyeball, so it never hurt. It didn't swing you away. Okay? But if you flatten it or curve it or whatever you needed to do, just like putting on a contact lens, you now have better permanent vision. It's all about the parabola. It's all about the focus point of where that focal point of the lens is going to be. Telescopes use parabolas. A mirror in a convenience store that looks around the corner is a convex parabola. It's just the mirror's on the back side instead of the front side. That's how you can see around corners. So the x squared is kind of important. X to the third. The parent function for x to the third, polynomial equation. I'm going to leave x squared there for a second. When you think of x squared, good old parent function x to the second, no matter what you square, it's always going to be positive, unless you put the negative up front, but it's always going to be positive. That's why it goes like this. On the negative side, it's the positive, square positive, you get a positive. It'll look like this. X to the third. I'm using g of x so I can do something different. X to the third. So -3, -2, -1, 1, 2, 3. -3 on my picture is not that useful. Because if I plug in -3, parentheses, -3 to the third power, so that would be a negative to an odd exponent is going to be a negative. 3 to the third is 27. This only goes to -7, so it's way off the scale. It's not going to fit on that graph, so that's why I'm making a different set of arithmetic units. So I'm going to actually start with -2. -2 to the third is -8. -2 times -2 times -2, -8. So it's down here. -2 goes in, we get -8. -1 goes in. -1 to the third. A negative to an odd is going to say -1 to the third is still 1. -1 times -1 times -1 is -1. So we get -1 for x, -1 for y. It's right here. Zero. Well, 0 to the third is 0. So they share a point right there. They share the origin. Have the origin in common. G of 1. Now, +1 to the third. is just 1. So they share another point. 1, 1. And then you go G of 2. 2 to the third is positive 8. So the honeymoon is over. They stop sharing. That's up there at 2, 8. So on this left-hand side, it's down below. And then over here on the right-hand side, it's up above. And that's the parent curve of an x to the third function, a cubic. Now, a cube is 3-dimensional. Hey, that's a power of 3, it's 3-dimensional. Okay, that's why it's called a cube. What we're able to do with the cubic is eventually you might see a cubic that looks like this. That's also a cubic. What makes it a cubic is this. The fundamental theorem of algebra that I did mention the other day is if you have a first degree equation like x to the first, then it has exactly one solution. So if you have an equation with x to the first, there's one answer. When you have x squared, power of 2, then there's 2 answers. X to the third will have 3 answers. So even though it only has one x-intercept, that means it's one x-intercept that happens 3 times. It's called a triple root. Okay. That's, again, something we'll talk about. This is a picture of an x to the third because it intersects the x-axis 3 times. It has 3 solutions if you let the equation equal 0. So this x to the third picture, g of x equals x to the third, this one is the parent function. So what we'll make when we get to here? But we start with something that looks like that and manipulate. And you can see that's in chapter 3. The rational function, 1 over x. Rational, root word is ratio, fractions. So x is in the denominator. X is in the denominator. We got a variable down below. That's going to mess up something called the domain. These first 3 are polynomial functions. X to the first, x squared, x to the third. When you have a power on the x, those are polynomials. The domain of a polynomial function, all real numbers. Anything you plug in from negative infinity to positive infinity is all good. They will work. Nothing that you plug in is going to cause any problems whatsoever. The function's defined for any number you could possibly think of for the first 3. Until we get to the problem causer, the little, piece of work here, the rational function. When we get to the rational function, 1 over x. Out of all the real numbers, you are not allowed to divide by 0. You cannot divide by the number 0. 5 divided by 0 is undefined. 0 divided by 5, perfectly fine. So here's the deal. 0 in the numerator over a number, like 0 over a 5. That's a 0. But when you have a number over 0, like 3 over 0, undefined. We will be discussing what happens when you have 0 over 0. We're not going to do it today, but we'll talk about it later. Because think about it. you've got, hey, 0 in the numerator, the answer must be 0. Wait a second, 0 in the denominator, the answer must be undefined. Well, make up your mind. Can't be both. So if it can't be both, it's got to be probably something else. So for this one, though, f of x equals 1 over x. So out of all the numbers that go forever to the left, which is negative infinity at the end over there, positive infinity to the right over there, what can you not have down there? 0. If you try to go f of 0, you get 1 over 0, and that's not allowed. That's undefined. It's not in the domain. The domain is what you're allowed to plug into the function. The domain is the x's. Domain is what goes in. Range is what comes out. Domain D, range R. D before R alphabetically. Domain is the x's. X before y. Y comes second. Domain goes with the x's. Range goes with the y's. What am I allowed to plug into this function? I can plug in all real numbers except x cannot equal 0. Now that's a lot to write down. We're going to do it differently when I show you more on Tuesday. For right now, that's just what it looks like. So what in the world happens at 0? Well, don't plug it in. If you try to plug it in, you can't put a point. You can't draw anything. So what happens is we do something called a vertical asymptote. At 0, there is something called a vertical, so it's a straight up and down line, asymptote. Asymptote. It's not my vocabulary, but I'm passing it on to you. Okay. So that means right here, take the straight edge and you would make, it's kind of like a wall that you cannot touch. You can't touch it. I'm going to stay on this side first. Now take a look. F of x is 1 over x. Let's plug in 1. 1 over 1 is just 1. So when 1 goes in, 1 comes out. Look what happens when we plug in 2. 1 over x is now 1 over 2. So when 2 goes in, we get a half. When 2 goes in, it's half as tall. The y value is 1/2. It's half the height of what happened at 1. And then when 3 goes in, 1 over x is now 1/3. So it's 1/3 of the original height when you plug in 1. It's approximately right about there. And when you plug in 4, 1 over 4 is at about 1/4. And then pretty soon, realistically, my pen is too fat to keep drawing over any given points. But you see, we can continue, and this is where it ties into the beginning of class, quantum mechanics. We can continue forever, and it's never, ever going to touch the x-axis. So even if you pick a huge number, a really, really huge, big old number, further on down the line, something like, I don't know, let's take like 10. Something huge. It's just 1/10. It's still a positive number that's above the x-axis. You plug in 100, it's 1/100, 100. 1,000, it's 1,000. A billion, it's still above the x-axis. You plug into Google, it's 1 Google. It's still higher than the x-axis. So what happens is, as you go to, and this is Isaac Newton stuff, you go to infinity. You cannot get to infinity, but you can approach it. As you approach infinity, the y value approaches 0. It never equals 0, but it approaches 0. In calculus, it doesn't matter what it equals. What matters is, what are you getting close to? So this way, it's doing this. It's like if you were a surfer and you were riding in on a wave, and that wave just kept on going forever. But you can't plug in 0. What if we plugged in and got close to 0? Like 1/2. F of 1/2 would be 1/1/2. So 1 divided by 1/2. How many times does a half go into a 1? I'll wait over here. 2 times. Remember, when you divide by a fraction, you multiply by the reciprocal. 1 divided by 1/2 is 1 times the reciprocal. You get a 2. Or how about this? 1 divided by a half of a dollar. 1 divided by 50 cents. 50 cents is 2.5 dimes. So when a half goes in, we're up here at 2. When you plug in a third or a fourth, when you plug in a fourth, we're up here at 4. When you plug in a 10th, you're up here at 10. When you plug in, you get really close. You plug in 100th, the y value is 100. You get closer to 0, you plug in 1,000, the y value is 1,000. The closer you get to 0, the bigger the y values grow to infinity. But the y values, the x values, are approaching 0. This graph can never touch the 0. It can just get infinitely close to 0. That's what the asymptote is. That means it can never touch that vertical x equals 0 line. But the graph is just infinitely getting closer and closer and just slides on up. Not parallel to it, because that would be the same direction. Just infinitely closer to it. That's what that little arrow helps us see. Now on this negative side, 1/-1 would be down here. 1/-2 would be a -1. 1/-3 would be a -1/3. It would be down below because you're plugging in negative numbers for x. 1/-1/2 would be a -2. 1/-1/4 would be a -4. It would be over here. And that's what rational expressions look like. So that's the parent function of a rational expression. Now, make sure you have your access. Danielle has the knowledge about make her uncomfortable. That's what we're. And real quick, I need to pull up the current web advisor, because I know people have added, and I want to call roll as accurately as I possibly can. So give me a quick 10 seconds here to roll the most accurate roster. Enjoy your 3-day weekend though, but you know, stay safe. Yeah, I think we'll. So, Josh Aguilar.
Here.
Gavin, Luis, Eduardo Montilla, Charles Compton, Francisco De Laura, Luis Heredia, Brian Lira, Marcelino Lopez, David Marcial, Dino Reyes, Alyssa Rios, Alma Rios, Ryan Sines, Ryan, and Kelsey Watson. And if I didn't call you, see me, make sure we get that covered. All right, have a good weekend. And I'll post wrapping paper, and I think that's all I got. Okay.
And it's right when the title of the.
Is there any?
You'll know when I'm finished. I'll make sure I know. All right, that's everything for 1.1.
Because for me, it's like, I can't really.
I know, yeah, I will always, because I don't overlap in terms of all the lectures. I've given out a homework, but I don't just say, all right, and here's the lecture for the entire chapter, figure it out. I'm always going over homework as part of my lecture. So when I'm finished giving you examples throughout the lecture about how the homework ties in, then when we get to the end of the examples on the homework pages, that's when I'm done with that section. That's when you should be able to do all of the homework in that section.
For section 1.
So I haven't even started any examples from the actual homework itself. This was just, hey, this is a lot of this you should already know, but if you haven't, this is a lot of the background of where it comes from. This is me trying to give you an idea of how I do things, how I teach, but we haven't really lectured on material yet. You really haven't. Yeah.
So as of right now, just have the notes.
Make sure you have your book. And if you want to take a look at the homework, you know, again, a lot of it is Algebra 2 based, not 103 based. Give it a try. You know,
You'll be sure to.
absolutely, always.
That's all right.
I'm here for roll. I have the on my map on my dog route.
Ryan?
Yeah.
Okay, thank you. Appreciate that.
You know, map, but
Let me turn off this.